If I had to make a list of all the things in quantum mechanics that is going to blow your mind, then one of the top ones is definitely going to be quantum tunneling. This is something that we do not really see in our usual day-to-day classical world, and if we ever saw something like this, we would consider it magic. For example, if I take a ball and I throw it on my wall, then I reasonably expect it to come reflected back. I threw the ball with a low velocity, the wall is very hard. What if I throw the ball on the wall and the ball just penetrates through the wall like some kind of a portal? Then that is something that would be very interesting. It is the stuff of science fiction. But that is what is happening in the microscopic world all the time. That is what powers the sun. That is what leads to many of the elements in the periodic table. That is what is being exploited in the electronic industry, in the construction of various complicated semiconductor devices. And that is what also helps us in looking into the microscopic world and scanning various kinds of atomic and molecular configurations. Yes, I am talking about something so magical and yet something that is happening in the microscopic world all the time. Quantum tunneling. Imagine a particle which is approaching a barrier with a certain kind of energy, but it doesn't have sufficient energy to overcome the barrier. The particle has an energy which is less than the barrier. I expect the particle to get reflected back, but in the quantum mechanical world, there is a probability that the particle will tunnel through. It will go to the other side. That is something completely bizarre, something that you or I would never expect in the classical world, in our classical physical models and theories, that a particle has some kind of an energy less than the potential barrier it is facing, and yet it is somehow able to penetrate through the potential barrier through some kind of a magic. But the truth is, this is not really magic. This is something that is a reflection of our quantum mechanical world. You see, in the quantum mechanical world, particles are not really particles. They are waves. They are wave function solutions of the Schrödinger equation. And when these waves approach a barrier, there is always a probability that the wave or a portion of the wave can penetrate through it. Because of this reason, we see phenomena like in the context of the microscopic world. In this video, I'm going to derive that quantum mechanical probability. I'm going to solve the Schrödinger equation for this kind of a system. I'm going to apply the necessary boundary conditions. I'm going to do a lot of mathematics, but at the end of it, I will show you that there is a probability that in the quantum mechanical world, a particle can be found on the other side, even though it doesn't have sufficient energy to overcome this particular barrier. There's going to be a lot of mathematics involved, but at the end of it, you will see something completely magical that is happening in our world all the time. Let's begin. If you are a student preparing for various examinations in India, like Physics IIT JAM, NET or GATE Physics, then you can find extremely dedicated courses, both live and recorded courses, on our platform elevateclasses.in. Alright, so in this problem, we have a very simple situation of a rectangular potential barrier of fixed width and fixed height, and a particle approaching it with energy less than the barrier height. What we want to do is we want to solve the Schrödinger equation, we want to apply the boundary conditions, and then from the boundary conditions obtain the transmission coefficient or the tunneling probability. So we have three distinct regions here: region number 1, region number 2, and region number 3. Let's get started. So in region number 1, we have a certain Schrödinger equation. In region number 2 and 3 also, we have Schrödinger equation. So let's just copy paste it to save some time, because this is the time independent Schrödinger equation. Alright, it has the same form in all these cases. The only difference is the nature of the potential here. In region number 1 and region number 3, the potential V is equal to 0. Alright. And in region number 2, V is equal to V0, which is greater than E. Alright, that is the difference. So this can be written in this manner: d2 psi upon dx2 plus I would say k1 square psi is equal to 0, where, let me define all these different kinds of constants, okay? Where, let me define it here, k1 square is equal to 2m capital E upon h cross square. I hope that you are familiar with all the constants involved here. M is the mass of the particle, h cross is Planck's constant upon 2 pi, E is the energy of the particle. All right, k1 is essentially 2m E upon h cross square if you look at this expression. And here I am going to write this as d2 psi upon dx2 minus k2 square psi is equal to 0, where k2 square is equal to 2m upon h cross square v0 minus E. I have written v0 minus E because v0 is greater than E. So I just replace their positions, and when I replace their positions, a minus sign gets introduced here. And in the same way, for region number 3 also, we have exactly this situation as the first case scenario. Just copy paste it here. Now, if you look at these differential equations, these are very standard differential equations that we regularly face in quantum mechanics, and I hope by now most of you are familiar with the nature of their standard solutions. So for differential equations of this form, the standard solution is an oscillatory solution whose general solution is written as, so let me write it as psi1, okay? Psi1 for the solution of the Schrodinger equation in region 1 as A e to the power iota k1x plus B e to the power minus iota k1x, right? And in region number 2, for differential equations of this form, we end up getting exponential solutions. Both exponential increasing and decreasing terms are involved. So psi2 is the solution of the Schrodinger equation in region 2 is c e to the power k2x plus d e to the power minus k2x. And similarly, in region number 3, we have the solution of the Schrodinger equation psi3 is equal to abcd e to the power iota k1x. I am going to write k1 because it's the same k1 here in this expression, plus f e to the power minus iota k1x. Okay, these are the standard solutions of these kinds of differential equations that we encounter on a regular basis in quantum mechanics. So it's better that if you keep a note of them or remember them, because you will see these differential equations all the time and you will have to bring from memory the nature of the standard solutions. So this is an oscillatory solution. So is this an oscillatory solution. However, the middle region is essentially exponential. It ends up being exponentially decaying solution. So what it means is that in region number 1, if you look at it, we have a oscillatory solution associated with the approaching particle, which we can call as incident wave. But if you look here, there are two distinct solutions. One is a solution moving forward direction, the other is a solution moving in the backward direction. So the first solution represents a wave that is moving in the forward direction, and the second solution represents a wave which is reflected back. So the incident wave and the reflected wave, all right, because once the wave approaches the barrier, it strikes the barrier, it is going to, some portion of it is going to get reflected back. So a e to the power iota k1x is the incident wave, b e to the power minus iota k1x is the reflected wave. Now, if you look at exponential function, that is where we have an exponential solution in region number 2, and in region number 3, also we have oscillatory solution. Okay, in region number 3 also we have oscillatory solutions. However, in region number 3, there cannot be a reflected wave because there is nothing ahead of it. It is just a free particle up to infinity. So if there is nothing ahead of this wave, there is no possibility of reflection. So therefore, we have to assume that this is equal to 0. You see, when the solutions of the Schrodinger equation are analyzed, we have to make sure that it satisfies different kinds of conditions given in that particular physical system. So in region number 1, there is both possibility of incident particle, reflected particle, But in region number 3, there is only a possible of a transmitted particle, no reflected particle, because there's nothing ahead of it. Okay, so these are the nature of the solutions, but we are interested in these constants. Okay, why? Because if I'm interested in tunneling, this is what I'm interested in this particular lecture, tunneling, then I am interested in the ratio of E upon A. The ratio of E upon A will give us the ratio of the amplitude of the transmitted wave versus the incident wave, and that would give us the probability of tunneling. All right. The ratio of the amplitude of the transmitted wave and the incident wave will give us an idea about transmission coefficient, which can be used later on to calculate tunneling probability. So let us start. How do we do that? We apply the boundary conditions at x is equal to 0 and x is equal to a. Let's start. Boundary conditions, very important. So there has to be a continuity of the solutions across the region as well as its derivatives. So the wave function as well as the derivatives of the wave function has to be continuous across the region, and specifically at x is equal to 0 and x is equal to a. So that means the wave function solution at x is equal to 0 for region number 1 must be equal to the wave function solution in region number 2 also at x is equal to 0. Make sense? All right. Now this would lead to a very simple equation: a e to the power 0 plus b e to the power 0 is equal to c e to the power 0 plus d e to the power 0. That leads to a plus b is equal to c plus d. All right. I'm going to mention this as point number 1. Let's move on to its derivatives. The same kind of continuity must also be maintained by its derivatives. So d psi 1 upon dx at x is equal to 0 and d psi 2 upon dx at x is equal to 0 must also be continuous. So what does this mean? It means that if you take the derivative of psi 1, you will get iota k1 a e to the power iota k1 at x is equal to 0, so e to the power 0, plus you have minus iota k1 b e to the power 0. Similarly, here we have k2 c e to the power 0 minus k2 d e to the power 0. This leads to iota k1 a minus b is equal to k2 c minus d. This becomes a minus b is equal to, this is k2 upon k1, but since there is an iota in the denominator, I should have minus iota in the numerator, c minus d. Let's say that this is point number 2. Same thing I want to do at boundary of x is equal to a. So at x is equal to a, so this was at x is equal to 0. Now I want to do the same at x is equal to a. So we will get psi 2 at x is equal to a must be equal to psi 3 at x is equal to a. So what is psi 2 at x is equal to a? So c e to the power k2a plus d e to the power minus k2a is equal to e to the power iota k1a. All right, this is the equation. I'm going to mention this as, or mark this as point number 3. Same thing with derivatives. D psi 2 upon dx at x is equal to a is equal to d psi 3 upon dx at x is equal to a. I should get k2 c e to the power k2a minus k2 d e to the power minus k2a is equal to iota k1 e to the power iota k1a. This becomes k2 c minus d or I should say C e to the power k2a minus d e to the power minus k2a is equal to iota k1 e to the power iota k1a, which can be rewritten as C e to the power k2a minus d e to the power minus k2a is equal to iota k1 upon k2 e to the power iota k1a. Keep in mind that this is going to be a little bit of a mathematically lengthy and laborious calculation, but it's okay. I'm going to explain all the steps to you so that if you are deriving this, you will find that we will reach the final conclusion in no time. So what we have done is we have written down the Schrodinger equation in region 1, 2, 3 and the nature of its solutions, and then applied the boundary conditions to get these three distinct equations: 1, equation 2, equation number 3 and 4. Now I want to find out the ratio of E upon A, right? Because that would give us the ratio of transmission between the waves, which is a transmitted wave, upon the incident wave. So to do that, let's add the equations 3 and 4. Add equation number 3 and 4. This would lead to C e to the power k2a d e to the power minus k2a plus C e to the power k2a minus d e to the power minus k2a is equal to capital E to the power iota k1a plus iota k1 upon k2 capital E to the power iota k1a. You can see here that these two terms gets cancelled and we are left with 2c e to the power k2a, which is equal to, if I take this as common, capital E 1 plus iota k1 upon k2 e to the power iota k1a. If I write this in its final form, this becomes capital E upon 2, 1 plus iota k1 upon k2 e to the power iota k1a minus k2a, right? Minus k2a. That's it. This is point number 5. Same thing, let us subtract 4 from 3 again. Okay, I'm going to do the same thing here. Control C and V, just copy paste it, because I am going to subtract 4 from 3. So subtract 4 from 3. In that situation, there would be a minus sign here, plus sign here, and a minus sign here. So it would mean that these two get cancelled out, and instead of these expression, I will have 2d to the power minus k2a, and this, there will be a minus sign here, and we will get d is equal to, this would become plus. That's it. This is point number 6. You see how at least the steps are very simple. It's just that the equations themselves may look a little bit complicated. By the way, this shouldn't exist because I have taken it to the other side. So there is no exponential term here. So now that we have obtained C and D, let us plug them into equation number 1. A plus B equals C plus D. Equation number 1. Okay. Use 0.5 and 6 in equation number 1. Equation number 1 was A plus B equals C plus D. So what is C plus D? C I'm going to use from here straight away. This is capital E upon 2, 1 plus iota k1 upon k2 e to the power iota k1a minus k2a, that is C. And D is capital E upon 2, 1 minus iota k1 upon k2 e to the power iota k1a plus K2A. That is all, right? So let's simplify this and see what we get. Well, we can take out some of these terms. Okay, let's take out these terms first. So this should give us E upon 2, right? And e to the power iota K1A minus K2A. And I also have e to the power iota K1A plus K2A common, right? Now let's look at the other terms, plus e upon 2 iota K1 upon K2, and here we again have e to the power iota K1A minus K2A minus e to the power iota K1A plus K2A. Okay, I have separated the terms and taken common. The reason I've taken common is because we can write these exponentials in the forms of sines and cosine hyperbolic functions. Okay, so you must be aware that sine hyperbolic something is equal to e to the power x minus e to the power minus x upon 2, while cos hyperbolic x is e to the power x plus e to the power minus x upon 2. Okay, I'm going to use these expressions here, but let us take something out first. Okay, so here I want to take e to the power 2, e to the power, I should say, K2A plus e to the power minus K2A. Okay, I am taking e to the power iota K1A out of this bracket. And here I am going to write this as e to the power K2A minus e to the power minus K2A, and again e to the power iota K1A I have taken out of the bracket. So now if I take this as common, e to the power 2, sorry, capital E upon 2, e to the power iota K1A, then this expression is nothing but twice of cos hyperbolic K2A, right? And this expression is nothing but twice of sine hyperbolic K2A, right? Now the 2's get cancelled and we are left with a plus b, or if I divide the whole thing by a, 1 plus b upon a is equal to e upon, there is a term that I forgot to write. There was this term also, right? So here in this particular expression, there was this term of iota K1 upon K2. Okay, so this becomes E upon capital A, e to the power iota K1A, and within brackets I have cos hyperbolic K2A minus iota K1 upon K2 sine hyperbolic K2A. That's it. Finally, we have achieved something till this point. All right, so let's say that this is equation number 7. Okay, equation number 7. And I want to do the same thing here. I want to use 5 and 6 in equation number 2 now. Use 5 and 6 in equation number 2. So let's say that I take this equation number 2 from here. Okay, this was the equation number 2. Remember, let's just copy paste it. Oh, it's working now. Fine. Okay. Let's bring it down. So this is equation number 2. You see, it's a little bit of a mathematically lengthy problem. No problem. No issues. Okay, so 5 and 6. Point number 5, this one. And point number 6, this one. So essentially this equation, right? C plus D. So instead of C minus D, I'm going to write this whole thing. Okay. Again, let me copy paste it here. Okay. So here I'm going to write A minus B is equal to minus iota K2 upon K1, and then we will have C minus D. So minus will mean that I should include a negative sign in the middle. All right, now let us try to simplify this also in a very similar fashion. If I try to simplify this in a similar manner, A minus B is equal to minus iota K2 upon K1. Let's take E by 2 out of the picture, and let us also take e to the power iota K1A out of the picture. Then we are left with 1 plus iota K1 upon K2 e to the power minus K2A minus 1 minus iota K1 upon K2 e to the power K2A. Let us try to simplify this and see what we get. A minus B is equal to all right, so if we simplify it, one term would be minus e to the power K2A and minus e to the power minus K2A, right, for this and this. Okay, I have taken the second term and placed it in a first manner as a first term. This is the expression we have. And next, iota K1 upon K2 would be common. Here I am going to write e to the power K2A plus e to the power minus K2A. Again, using the sine and the cosine hyperbolic function, this is simply going to become minus twice sine hyperbolic K2A plus iota K1 upon K2 times twice cos hyperbolic K2A. Okay, the 2 gets cancelled, and if I divide the entire equation by capital A, this becomes 1 minus B upon A, and here I have E upon A, e to the power iota K1A. There's a negative sign here, and if I take this term inside, what do I get? Let us also take the negative sign inside. Okay, so the negative and the negative becomes positive, and we are left with iota K2 upon K1 sine hyperbolic K2A, and then here K2 upon K1 and K1 upon K2 gets cancelled. There's a negative sign, but there's an iota, and then there's an iota becomes minus 1, minus 1, minus 1, becomes plus. So this is just cos hyperbolic K2A. So finally, we have our expression 1 minus B upon A is equal to E upon A exponential iota K1A cos hyperbolic K2A plus iota K2 upon K1 sine hyperbolic K2A. Let's mark this as equation number 8. We are almost there. We are almost there. Just a few steps are left. Let us now add equation number 7 and equation number 8 and see what we get. Add equation number 7 and equation number 8. Okay, so this is equation number 8. Okay, let's bring it here, and also let's bring equation number 7. Let's add them. Okay, so if we add both of them, what do we get? First of all, this gets cancelled, right? And second of all, on the left hand side we have 2, in the right hand side I can take capital E upon A common, e to the power minus iota K1A also common, and then here we will have this will get added, 2 cos hyperbolic k2a, and then we will have plus iota, we will have plus sine hyperbolic k2a as common, and here we will have iota k2 upon k1 minus iota k1 upon k2. Okay, now let's try to find out what is the meaning of this particular expression. We can calculate it by this side. Iota k2 upon k1 minus iota k1 upon k2 can be written as, in the denominator we have k1 k2, and in the numerator I have iota k2 square minus iota k1 square, which will come out to be iota. So if I write it like this, iota k2 square minus k1 square upon k1 k2. Okay, so the final expression can be written in this particular manner, that if I take E upon A to one side and I take the whole expression to the other side and write it here in the right hand side, this simply becomes 2. This goes to the other side, so it becomes e to the power minus iota k1a, and this is just cos hyperbolic k2a, and this is plus iota k2 square minus k1 square upon k1 k2 sine hyperbolic k2a. Because the whole thing has been taken to the other side, there is a minus 1 to the power. Alright, so we are almost near our end. So just hold on, be patient. We are almost near the end of the derivation. We are about to get a very simple expression for tunneling probability. Why? Because as I said, E is the amplitude of the transmitted wave and A is the amplitude of the incident wave. Alright, we have a transmitted wave here and we have an incident wave here. The ratio of their amplitudes gives us an idea about the transmission coefficient, essentially, right? Not exactly, we have to take a mod square of it. So if I take a mod square of this E upon A, I will get the transmission or the tunneling coefficient or tunneling probability. So what is the probability associated with this incident wave to tunnel through? That is given by amplitude of the transmitted wave upon amplitude of the incident wave mod square. You do understand what a mod square means, right? Whenever we are dealing with these kind of complex functions, a complex conjugate multiplied to the function itself will basically give you a mod square. Okay, so if I take a mod square, what happens is the moment you take a mod square of a function, so if you have an iota, the complex conjugate is replaced by minus iota. So one term, we have 2 times 2, so this becomes 4. We have e to the power minus iota k1a and e to the power iota k1a. We will have one expression 2 cos hyperbolic k2a plus iota k2 square minus k1 square sine hyperbolic k2a upon k1 k2, right? And we will have another term exactly like this multiplied to this expression, but substituted with minus iota here. There's a minus sign here. Okay, because iota gets replaced with minus iota. So this gets cancelled, and if you look at this particular expression, we will have, what is this? This is a plus b into a minus b. That's it, which is a square minus b square. So I should get 4 cos hyperbolic square k2a minus b square, so whole thing square, which involves iota. Iota square comes out to be minus 1. So minus minus becomes plus. Therefore, I get k2 square minus k1 square upon k1 k2 whole square sine hyperbolic k2a. Alright, and again, of course, there was a to the power minus 1 here, minus 1, minus 1. So this becomes to the power minus 1. Here I can make one further substitution, that cos hyperbolic square k2a is basically equal to 1 plus sine hyperbolic square k2a. Okay, if I make that substitution, this simplifies to 4 plus 4 sine hyperbolic square k2a plus k2 square minus k1 square upon k1 k2 whole square sine hyperbolic square. There was supposed to be square here, okay, k2a. If I add them, mathematical equations are the cornerstone of physics. They are the language of physics, you know. This is how physics speaks to us. This is how physics translates into reality, through these mathematical equations. And if you want to have an understanding of how physics is behaving, why physics is behaving the way it is behaving, then we have to get comfortable with extremely complicated mathematical equations, even though it is hard. I know it is hard. It is hard to keep track of all the terms, the pluses and the minuses. You make a small mistake here and there, all your hard work is gone. So we have to be a little bit of a patient and sort of show a little bit of care to the subject by giving attention to the mathematical equations. So 4 plus, if I take sine as common, I should basically end up getting, in the denominator here, k1 square k2 square. In the numerator we will have sine hyperbolic square k2a, and in the numerator we will have 4 k1 square k2 square. If I open up this term, this would give me k1 to the power 4 plus k2 to the power 4 minus 2 k1 square k2 square. All right, so this is a minus sign. If this gets cancelled, I am left with 2 here. 4 minus 2 is just plus 2. And what is k1 to the power 4 plus k2 to the power 4 plus 2 k1 square k2 square? That is just k1 square plus k2 square whole square, right? So this therefore becomes 4 plus k1 square plus k2 square whole square upon k1 square k2 square sine hyperbolic square k2a. So there is a negative power of minus 1. So if I take the 4 out of this, the 4 and the 4 will get cancelled, because here there is a negative power of minus 1. So this can further be written as 1 plus 1 by 4 k1 square plus k2 square whole square upon 4 k1 square k2 square sine hyperbolic square k2a to the power minus 1. This is the tunneling probability, which you can see by now. It's not exactly 0. In classical mechanics, we have no such analogy. Okay, in classical mechanics, particles do not penetrate potentials if it doesn't have sufficient energy. But there is a possibility in quantum mechanics for a particle to penetrate through a potential, even though it has energy less than the potential barrier. And this is seen from this non-zero expression. If there was no tunneling, T would come out to be 0, but there is tunneling, so T comes out to be non-zero. Let's further simplify to get the final answer. So here I can further simplify k1 square plus k2 square upon k1 square k2 square whole square, right? Do you remember what k1 and k2 are? If you remember, they are simply the wave numbers associated with the oscillatory waves in region 1 and the exponential function in region number 2. K1 is this, K2 is this. So let me just substitute them and see what we get after such a lengthy derivation. So K1 square is 2me upon h cross square. K2 square is 2m v naught minus e upon h cross square. and here I have 2me upon h cross square times 2 upon v0 minus e upon h cross square, and there is a square term here. Okay, so if you look at this expression, 2m upon h cross square, 2m upon h cross square, take common, take it out, this gets cancelled with this. Okay, and you are essentially left with, in the numerator you have e plus v0 minus e whole square. Okay, in the denominator you have e times v0 minus e. So here again e and e gets cancelled, and this is quite simply put v0 square upon e v0 minus e. Very simple expression. So if I substitute this here, this is simply going to become, or tunneling probability is equal to, because there is a negative power here, let me write this in the denominator. This is going to become 1 plus, so this is nothing but v0 square upon 4e v0 minus e sine hyperbolic square k2a. Okay, by the way, k2a is, you know what it is. So this is the most general expression for the tunneling probability without making any kind of further assumptions. Now you probably want a little bit of a more simpler expression, I understand, and we can do that. We can do that by making a few assumptions here. Okay, so let's assume that E is very, very less compared to V0. Okay, if we make that assumption, if E is very, very less compared to V0, then if you take a look at K2, what is K2? K2 is simply 2m V0 minus E upon h cross square, right? And if you take a look at sine hyperbolic K2a, sine hyperbolic K2a can be written as e to the power K2a minus e to the power minus K2a upon 2, right? But since we have sine hyperbolic square, we have a square here. Okay, now if E is very less compared to V0, then e to the power K2a would be very large and e to the power minus K2a would be very small. So under this kind of an approximation, if energy of the particle is very less, then e to the power minus K2a is also going to be very less, and we can neglect it almost. And if we neglect it, because in comparison to this, it is very small, because it's an exponential function, right? The moment you take exponential something, it becomes very large. The moment you take exponential to the power negative something, it becomes very small. So this is essentially nothing but e to the power 2k2a, approximately speaking, okay? Approximately speaking, upon 4. So for this approximation, if I make a substitution in the expression that we have obtained, this very lengthy, complicated looking expression that we have obtained, it simply ends up becoming capital T is equal to 1 upon 1 plus V0 square upon 4 capital E V0 minus E, and here we have e to the power 2k2a upon 4. Okay, 4 and 4, you end up getting 16. Now again, further approximation, here this looks like a very large number because you have exponential to the power positive something plus 1. Another approximation I'm going to make here is that we have something like 1 upon 1 plus something. It's a very large number. I'm just approximating it to 1 upon this, okay? Because I want to simplify the whole expression to get something that resembles an approximate answer but looks mathematically simple, okay? If we do that, this simply ends up becoming, it goes to the top, we have 16e V0 minus e upon V0 square e to the power minus 2k2a. All right, now we are almost there, all our hard work is going to be fruitful. It is going to give us something very interesting. So 16 e to the power V0 is one expression, and then we have 1 minus e to the power V0 e to the power minus 2k2a. That's it. This is the more simplistic expression. If you get a question in quantum tunneling, then majority of the times this is the expression that is used. This is the more general expression, but for particles having very less energy or particles where the barrier width is large, because we are talking about exponential decays, right? Then we can use this particular expression. Okay, so you can see that the tunneling probability is directly proportional to e to the power minus 2k2a, where what is k2? K2 is nothing but 2m v0 minus e upon h cross square root over. That's it. That's k2. Okay. And what is a? A is the width of the barrier. Okay. That's it. It is not zero. This is not zero. It's an exponential decay, yes, but it is not zero. And because it is not zero, in the quantum mechanical world, whenever we are dealing with electrons or other kinds of particles, we see that there is a probability of tunneling through. When alpha particles experience tunneling, we end up getting alpha decay processes. Because if you look at alpha decay processes, the alpha particles do not really have sufficient energy to overcome the Coulombic potential barrier, and yet they do. And that is, they do because of quantum tunneling. That is why we have alpha decay processes, radioactive processes. When we look at nuclear fusion, we have the similar thing, that we cannot have two protons combining together or fusing together to create a bigger atom in as much likelihood if there was no quantum tunneling. There is a certain element of quantum tunneling that sort of accelerates this process, makes it more likely to happen. So this is the quantum tunneling that I'm talking about, where a particle, even though it has energy less than the potential barrier, still has a probability of tunneling through. I will share these notes in the description as a PDF. If you are interested, you can take a look at the notes. That is all for today. Thank you so much, guys. Have a nice day. Take care. Bye-bye.